All right. Hello, everybody. My name is Ryley Hill. Scott did a great job introducing this topic, and so I'm going to carry on the discussion of some of these SPT protoclusters. And in particular, I want to talk a bit more about the faint starlight that we're finally managing to observe in some of these brightest star-forming protoclusters. So, I mean, we don't need too much of an introduction of what a protocluster is. It's a collection of galaxies that are going to become a full-blown galaxy cluster by redshift 0. And some of the reasons why these protoclusters are so interesting to study is because they really represent the most active phase of structure formation. So here I'm just showing a plot of the cluster's mass as a function of the age of the universe, and you can really see that this period here over the first couple billion years, you've got this massive increase in the cluster mass, and this phase right here in structure formation is sort of represents a peak in galaxy mergers and interactions. This is when we expect the most massive galaxies to have formed, and also that's in these protocluster regions we expect to find the bulk of the star formation in the early universe. So this is really, all of the astrophysics that we love to study, all wrapped up into one big giant bundle and it's great laboratories for studying the details of structure formation. But it's really hard to right now. We don't really have a great handle on the details of what's going on here. I mean, here I'm just showing a couple. These are some SED selected clusters from the South Pole Telescope survey, and these are some of the highest redshift X-ray selected clusters, but they're really not probing this region of interest yet. And so we really don't quite know when and why the galaxy environmental effects took place, what drove the star formation rates in the early universe in these dense regions. And then we also know from looking at local clusters that the star formation rate has slowed down quite dramatically over cosmic history. And so what caused people like to call this quenching. So what were the processes that made galaxies quench? So these are all things that we hope to get a better handle on by studying the population of galaxy clusters out here in the early universe. And so how do you find these distant galaxy clusters? Well, as we heard from the last talk, you can turn to surveys of the cosmic microwave background, but I like to call this actually the cosmic microwave foreground. So here's a picture of the taken by Planck of the CMB, although in this version I have not taken out the galaxy or any of the foreground stuff, because here you can actually find some very interesting objects. In fact, if you look for the brightest peaks in this image in maps of the cosmic microwave background, what you'll find are things that are so bright they can only be gravitational lenses like this one down here, or groups of star forming galaxies like up here. And so as Scott mentioned in the last talk, looking through the South Pole Telescope survey of the millimeter sky has uncovered a whole handful of these concentrations of star-forming galaxies. Just to give the kind of the scope of what's going on here. Here's the size of the CMB survey beam. So this is what you'd see in your CMB surveys, and then when you follow these rather uninteresting blobs up with higher resolution telescopes, these protoclusters tend to break up into concentrations of galaxies, or concentrations of sources, submillimeter sources that look like this. So these are the protocluster candidates that we're interested in, and we're going to follow up with even higher resolution. And I'm just going to point out one interesting thing about these submillimeter selected protoclusters is that here I'm showing the star formation rate of the South Pole selected protoclusters that Scott was talking about in the previous talk, and this is just compared with some of the literature protoclusters out there, and they really do seem to have quite dramatic star formation rates. And then here's another version of that plot compared to simulations. And then you can see here that they're basically, the star formation rates that we're observing are quite a lot higher than what seems to be predicted in simulations. So there's a lot of interest in this sample. All right, so now I'm going to turn to SBT2349, which, as we've heard, was the brightest of the SBT selected protoclusters. This is protocluster at redshift 4. The total star formation rate is something like 10,000 solar masses per year. And so, I mean, this white circle is in some sense, this is the size of the South Pole telescope's beam, and here it's been resolved a little bit further. And if we zoom in even more with ALMA, we see this exciting concentration of submillimeter galaxies. We found about 20 submillimeter galaxies in this region alone so far. And in particular here in the middle, there seems to be, this is what we might call the brightest cluster galaxy, or a BCG. And so just to put this into context, I mean, this is a size, this size is about 100 kiloparsecs. And that's about the size of the Milky Way's halo. So I just kind of drew a little Milky Way in there. And so if you lived in a galaxy in this region over 10 billion years ago, and you looked up into the sky, instead of seeing two puny little Magellanic clouds, you would instead see 20 giant galaxies all in the process of colliding with one another. So it would be a pretty exciting time to live. And we've asked, what happens when you cram 20 galaxies within 100 kiloparsecs? And as we saw, the answer is as a mega merger. Basically, all these galaxies are expected to merge with each other over the course of the next 100 million years, and form what we expect to be a BCG. And it's kind of interesting because we know that BCGs formed most of their stars quite a long time ago, but here we're getting the first glimpse into the ingredients of those BCGs, and as soon as they all merge, I mean, all of the information into what went into a BCG is going to get buried into this mega merger. So here we've got a glimpse of a BCG before everything sort of gets mixed together. All right, so far I've just been showing you pictures of the millimeter wavelength light taken by ALMA. So this is light sensitive to star formation. But what about the stars themselves? So the stars are visible at much shorter wavelengths, at rest frame optical wavelengths. So what's happening with the stars inside this protocluster? So to answer that, we observed this protocluster 2349 with the Hubble Space Telescope and with Spitzer. So each blue square here is just showing you the positions of the ALMA detected submillimeter galaxies. And as you can see, when we, after 2 orbits of HST and lots of integration time with Spitzer, I mean, this field doesn't look particularly remarkable, and that's just because these galaxies are producing so many stars, they're so dusty that it's obscuring most of the stellar light. So most of the, all of the excitement's happening in the millimeter. In the optical, you don't see too much, but this still is very good information from this picture. We can get a handle on the stellar masses of these galaxies by measuring their optical rest frame optical brightness and doing some SED modeling. And so that's exactly what we did. And so here's what this galaxy protocluster looks like on the so-called galaxy main sequence. This is just when you look at the star formation rate of each galaxy versus the stellar mass. So in pink, these are all of the 2349 protocluster galaxies. And then in gray in the background, I'm showing some field galaxies around the same redshift. And so you can see that the galaxies in this protocluster don't look particularly different from the field galaxies at the same redshift. However, if instead we look at this is called the depletion time scale. So this is the ratio of the gas masses to the star formation rates as a function of stellar mass. This is effectively telling you, how long can these galaxies sustain this much star formation if they're not going to be, thanks. How long can these galaxies sustain star formation at this rate if they're not going to be fueled with any, or if they're not going to be provided with any more fuel? And so you can see they have much shorter gas depletion timescales compared to field galaxies, which is maybe not so surprising because they're forming so many stars at once. But so this is kind of one difference we see in this dense region compared to the field, which is kind of interesting because if you look at the main sequence, they don't look very different from the field. All right, so we also had looked at the this is the stellar mass profile of 2349. So this is the total stellar mass of the protocluster as a function of radius out to about 1 megaparsec. And you can see, and then this is compared to typical redshift 1 galaxy clusters. So you can see the shape appears to be pretty similar to this redshift 1 galaxy cluster. But we know that all of these galaxies are going to merge in a blink of an eye in terms of cosmic time. So basically it's just going to look like this. But this is interesting because, here the BCG is basically already formed, by redshift 4. And so, what's going to happen to this protocluster as time goes on? Well, if it's going to look like a redshift 1 cluster, then it's going to need to grow, up here at the at larger distances. And now we don't know yet if this curve out here is suffering from completeness. There's probably lots of other galaxies out there within this region that we haven't detected yet because we've only been targeting millimeter galaxies. But in any case, the take-home message is that the most massive galaxy in this protocluster has already formed by redshift 4, and this is sort of what we expect from downsizing. So this fits into the picture of downsizing, where the biggest galaxies form first, and then the smaller galaxies form later. And so we're basically seeing downsizing in action. All right, so that's the end of my talk. Thank you.